Did you go to GHC?
Yes.
Yeah, both of you?
Yeah. Yeah. I got an offer.
Yeah, from
Full-time from Northrop Grumman.
Northrop Grumman? Yeah.
So I start next September.
Congratulations, yeah.
Thank you. Thank you.
You start next
September.
a year from now? They booked you right now?
Yeah, they were
Wow,
like,
they really want you.
they were like, enjoy the 2 semesters, enjoy the summer.
And this is not an internship, it's a real job.
Oh, full-time opportunity.
Congratulations, wow.
First job. Thank you.
And did you make sure they'll pay you well?
Well, yeah.
Or, but this was just, so there's another round of interviews or it's all done?
That's it. Yeah, they already sent me the offer and they're like, you have till October 9th to say yes or no, and that's it.
Awesome, yeah. Congratulations, that's fantastic, yeah. And what group will you be working with?
He just said he himself was like the manager. He's like, I'm hiring for my team, but he didn't really say specifically what it is. It's just like, oh, learn C. We're gonna work with embedded systems. And my role
Okay.
is software engineering, but I'm not sure what.
Okay, and you're fine with that?
Yes, I am. I mean, even if I'm not, I have a whole year to practice. So
Yeah.
Yeah.
No, Northrop Grumman. Northrop Grumman is one of the biggest defense contractors in the country.
Yes.
So they're a huge company.
Yeah. No, and they have in Melbourne, Florida. So that's what I like. I was like, okay.
Close, yeah, that's good. Yeah. They're in aerospace engineering. So, yeah. And how about you? You got an interview too?
No. I mainly just walked around, Expo talking to people. Because I'm still a sophomore.
How does it matter? Internships. You could have tried for internships.
That's true. I asked a lot of people about it, and they gave me some really good advice.
Yeah.
So hopefully I'll get one.
Next year. Okay. So we're going to finish up something that we started last time and we didn't quite finish. That was this problem with Madoka. Do you need me to turn on Zoom somewhere or you're okay?
I got the live stream going, so hopefully people like
See this already.
If you want to turn on Zoom, I can throw that link in there too. I know some people like going to Zoom, but I have that link for
Up to you. You tell me. I'm
think
okay
it
with.
should be fine like this.
Fine.
Yeah.
Because I'll be writing on the board as well.
Okay, yeah, I got the camera set up, so and it looks good, the angle.
Okay. All right. So quickly, we were talking last time about this problem of Madoka and the corruption scheme. The idea, well, in case you don't have it, the link is here. It's from VJudge. And the problem was as follows. You're told that there are 2 to the n players, right? And it's organized like a tournament, like a knockout tournament. And Madoka has this incredible power where he can decide beforehand who wins. And he makes the most money if the least numbered person wins, right? So if number 1, so whoever is numbered 1, if this person wins, Madoka makes the most amount of money. So he decides on this numbering in such a way that he gets the most money, but then there is this extra step where the organizers can go and change k of these games. By the way, the decision that Madoka makes on each game is whether the left player wins or the right player wins, right? And things are organized like a binary tree. And so the organizers can go and change k of these games and flip them from left to right. And the question is, how much can they mess up Madoka and his earnings? That's the question, right? So what's the least that Madoka can earn by this process? So I saw that one person did solve this problem on the weekend thing, right? I don't know, is that person here? You did? Okay, congratulations, that's good. So we'll kind of try to understand what it is that we are trying to do, and then hopefully this will become clear. In fact, all I'm going to discuss today is the analysis. The algorithm was pretty clear last time, I think, and hopefully that's what you followed. If you followed something else, that works as well. So this is an example from the problem set, which says if this is the organization, and if Madoka decides on all these red branches to win, so he decides over here it's the right child, over here it's the right child, and over here it's the left child. And if he did it this way, then number 1 would be the winner, and Madoka would make the most amount of money. And now, if the organizers are allowed to change one of these games, and if they flip here from, sorry, not that, they flip this guy here from left to right, sorry, right to left, then you see that 3 wins this game, and over here already the left one was going to win, and 3 continues to win, which means that Madoka can only get the money for number 3 to win, which is less than what number 1 could win, right? So Madoka's earnings went down, and the question really is this the best that Madoka can do, right? Really the input for the problem is simply the number of actually it's n where there are 2 to the n players, right? So in this case there are 4 players, so n will be given as 2, and you're also told this number k, which indicates how many games the organizer can flip. So there are 2 variables, n and k, and your job is to tell us what the answer is for that value of n and k. Nothing else is given. You're not given this tree, you're not given this tree, you're just supposed to figure this out. All right? Clearly, if k is 0, which means the organizers cannot change anything, then Madoka is going to fix things so that number 1 always wins. Right? So that's the best that can be done. So if k is 0, you always write down 1. Right? If k is not 0, then it's not going to be 1, and your job is to figure out what's the lowest that Madoka can make, right? All right, so it turns out the approach is we're going to assume that Madoka has set it up so that the left child always wins. Now, in the previous example, you had cases where the right child would win. We'll just flip them around and make sure that the game is standardized so that the left child always wins. Okay? It's not going to make any difference to the earnings. It's just that we're going to actually flip we're going to flip the part of the tree and make sure that the left child always wins. So then the question is, how many of these games should the organizer change from left child to right child? And that's what's going to give you the answer. But of course, we don't know which games the organizer is going to flip, and there are k possible games that they can fix, and there are n possible matches. Or rather, actually, it's n possible rounds. There are many more matches there, and we have to figure out which ones the organizer will change in order to find that answer. It turns out we don't need to figure all those details out. So here is what we're going to assume. We're going to assume that to start with, Madoka is going to set it up so that the left child always wins. We're going to, and if there are 2 different numbers, well, of course there are 2 different numbers for any game. We'll assume that the lower numbered one wins. So that's the only way Madoka can make sure that he makes the most amount of money, right? So we'll assume that, which means 1 is going to be the winner, and now in order to figure out what's the worst that can happen to Madoka's earnings, we have to figure out what's the highest number that's within distance k from player 1 in that tree, because then by flipping those games we can make that person the winner. Okay, so let me try and draw this picture. So the picture is that this is the tree, and we've set it up so that the left one always wins, and clearly we're going to set Madoka is going to have number 1 over here, so that 1 always wins, right? And anywhere else it's the same thing. We're going to assume that the left one wins over the right one, and that this number is smaller than that number. Okay, these are the assumptions we made here, right? So if this is I and j, we're going to assume that I is less than j, and that left always beats right. So this is the I is going to beat j. If you do it this way, then 1 is always going to be the winner, period, right? So this is Madoka's setting. And now we are asking, if the organizer can change k of these games, how bad can Madoka's earnings become? Now what we're going to do is we're going to figure out, remember, if k is 1, only one game can be flipped, which means we're going to look at all the people who played 1. These are the people who played with 1, and they all have some numbers. We'll pick the one that's worst, and that's the game we're going to flip. If, let's say, this is the one that has the worst number, we're going to flip this game, or the organizer would flip that game, and then this person would beat 1, and then this person would because the left one always wins, you're going to have that person become the winner. So all we have to do is to figure out how many nodes are at distance 1 from the left spine. This is the left spine. Okay, all of these nodes are part of the left spine. We're trying to figure out how many things are at distance 1. That's what we need for k equals 1. If we want k equals 2, what do? We're going to go one more step away and figure out how many different guys are at distance 2 away, and then 3 away, and then 4 away, and so on. Is that clear? So that's the question we are asking. We need to count how many neighbors are within a distance of k from player 1. And remember, player 1 is always along this left spine. Clear? So we have a perfectly balanced binary tree, and we are looking at this left spine, and we're asking how many nodes are at distance 1, distance 2, distance 3, and so on. We have to be a little bit careful because all these vertices have labels 1, because 1 always is the winner, right? 1 beats whoever this is and comes here. 1 plays this person and beats that person and is the winner, and so on. And all over the tree, the left child's number is transmitted above, right? That's clear. So we have to be a little bit careful. We can't just count the number of nodes. It's not that easy. We have to count this somewhat smartly. And we need to know what is the highest number that can win this game, which means we need to know what's the highest number that's within distance of k from the leftmost spine. Is this clear? All right, great. So for this, we have to, what's going on here? Where is my, okay. So we're going to do some analysis, and we're going to figure out what is the number of nodes that we can count. And among those, whoever has the highest number, that person is going to be the winner, for sure, if the organizer does the right things. So over here, how many players are in this tournament?
2 to the power height.
2 to the n, right? So if n is given and k is given to you, there are 2 to the n players. In the first round, these 2 to the n players play in pairs, and it becomes 2 to the n minus 1. Then again they play in pairs, becomes 2 to the n minus 2. So this level there is 2 to the n minus 1. Next level is 2 to the n minus 2, and so on until you get to 2 to the 0, which is 1. Right? So therefore, this bottommost layer is 2 to the n, which means there's n plus 1 different levels of the tree. Is that clear?
Yes.
Hi. So this is what's given to us, and our job is to do the count that we wanted to make, right? Okay, so we have this Madoka's tree. It has 2 to the n leaves here. It has 2 to the n minus 1 nodes in the previous level, 2 to the n minus 2 nodes in the previous level, and so on, all the way up to the top. And we're looking at this leftmost spine, and we're trying to figure out how many nodes are within distance k from it. So it turns out that we can write down the count in terms of what's called as a recurrence relation. I know you looked at recurrence relation somewhere in maybe your data structures class, and you never liked it. Well, it's not that hard, it turns out. So here is what we're going to do. We're going to say let t of n comma k be the quantity we're trying to figure out, which is what? It's the number of unique nodes or unique labels within distance k from what? From the spine, right? From this left spine. From the left spine. Does everyone understand what the left spine is? It's that branch of the tree that goes along the left branches, right? Okay, so we're going to try and write this as a recurrence relation. And the question is, how does this happen? So we know that at the top of the tree we have 1, that's the winner. Now the left child, of course, has to be 1 because the left child wins, right? And the right child has to be something else. We don't care what it is, but we know it's going to be different from 1, right? So what do we have here, and what do we have here? So we have 2 to the n leaves at the bottom. And since this is a perfectly balanced binary tree, how many are here? 2 to the power n minus 1, and same over here. Is that clear? This guy at the top is 1. That's the winner of the left half of the tournament. And here it's somebody else, and we don't really care. And this person is the winner in the right half of the tournament. The labels here are distinct from the labels here, right? So what we're going to do is we're going to say the count that we want comes from this side of the tree and from this side of the tree. And we'll add them up, and that'll be our answer. Is that clear? So we want t of n comma k. This is the count we want. This count is how many unique labels are within distance k from this leftmost spine, right? So some of it comes from here, some of it comes from here. And we'll take those two numbers and we'll add them up, and that'll be our answer. So let's figure out how much comes from here. Let's figure out how much comes from here, add them up. Good? Okay, so we want t of n comma k, and what is the contribution from the left and what is the contribution from the right? This is the question. Which one is easy? Let's do the right side. Okay, in the right side, 1 does not appear anywhere, right? And this guy here is at distance 1 from the leftmost spine. So therefore, if there is some other guy that is at distance k from this, it's at distance what from here? It's going to be 1 less, right? So I'm going to say, let's look at this tree, treat it like a different competition of 2 to the n minus 1 contestants, and figure out how many are at distance k minus 1 from the leftmost spine, and that's all we need. So from the right side, I am going to get t of n minus 1, k minus 1. It's n minus 1 because this subtree has 2 to the n minus 1 people, contestants. It's k minus 1 because I just want distance k minus 1 from here to here, so that the distance from here to here is k. Right? So this distance is k, this distance is k minus 1. Is that clear? Yeah? So this takes care of the right side. That's this guy here. Let's do the left side. It's not exactly the same on the left side. It's a little bit different. Why? Because the spine is on the left side, right? So if I look at this node and if I look at its right child, how far is it from the left spine? It's at distance 1. Whereas this guy's right child is at distance 2 from the left spine. So things here are different from things here. So if I want to count the left side, it's going to be t of, well, again, I have 2 to the n minus 1 contestants. So therefore, I'm going to have t of n minus 1 here, right? Because this looks like a contest on 2 to the n minus 1 players. And then I want things to be how far from this left spine? I still want it to be at distance k from the left spine. And that left spine is still here. So therefore, this is simply going to be k, not k minus 1. So this is what happens on the left side. This is what happens on the right side. Can I repeat any of this? Should I go over it again? Yes? Demba?
I think I get it, but I think it will also be helpful to go over k minus 1 and k, like our step.
Okay. Well, all of you understand why this should be n minus 1. Why?
Yes.
Because you have only half the people on both sides, right? This was a contest on half the people. This was another contest on half the people. You found the winner, and then they played, and that was the end of the championship, right? So there are only half the people here, and because we're talking about exponents, initially we had 2 to the n players. Now we have only 2 to the n minus 1 players in each, so this should be n minus 1. Then the question is, why is it k minus 1 here and why is it k here? If you look at the definition, we're counting how many of these guys are at distance k from the left spine. If you look at anything here, that distance to the left spine is the same as the distance in the big tree. That's why it's still k. Whereas if you look here, its distance from the left spine is 1 off from the real left spine we want. So I need to take k minus 1 and then add 1 more to it. Is that clear? Yeah.
What would be the base case?
Yeah, that's a good question, and that's what we're going to look at next, because we need that to finish the definition. Other questions?
So I guess we still have to break the n minus 1.
Yeah. This is simply a recurrence relation. We have work to do. I didn't say it was done. Okay, so let's write down the recurrence more cleanly here. We've got t of n comma k equals t of n minus 1 k minus 1 plus t of n minus 1 k. This is what we have. And Ricky pointed out that this looks exactly like the recurrence that you have for n choose k. This is the combinations formula. Okay, but the combinations formula is not going to work for you, and that's because of the question you just asked. The base case is not the same. Okay, so we have to solve the base case, and that is not clear at all. So we'll have to kind of work on it a little bit. But let's make sure that everyone is clear about this recurrence. And over here, we're going to assume that n, actually this whole thing is works well if n is at least as big as k. All right, actually it's even better if n is greater than k. Then this whole thing is clear, because if n is smaller than k, what happens? What happens if n is smaller than k? Or what if n is equal to k? Then?
You get to a point where like you've exhausted all the distance nodes that are possible. And
Right. So it's pretty much everything. If n is smaller than, remember this whole tree has only n plus 1 levels. And if n is smaller than k, if you want distance k, you're going to pick up everything. Right? So think of n equals 2, n equals think of, remember what we had on the previous slide. We can go back there. Come on. Yeah. This is the case when n equals what? 2, right? Because there are 4 players. So this is n equals 2. It looks something like this. And k, if we take k equals 1, which means the organizer can only change one game, then we were asking the question what happens, right? If k equals 1, then this is the left spine, and there are 2 of these nodes that are away from it. And if you include one of these, it becomes, you'll get the answer 3, which is the right answer. But if I take k equals 2, then I pick up everything, right? So if n is equal to k, you end up with the whole tree. And the whole tree has how many players? 2 to the n. So therefore, t of k comma k is simply 2 to the k. Or t of n comma n is 2 to the n, whichever you want to take. That's fine. That's one of the base cases. You can go down even lower, and there are some interesting lower level cases. So let's see how that happens. T of n comma 0. What's that? You have a tree with 2 to the n players, and the organizer cannot change anything.
So it's 1.
So it's 1, right? That's clear, right? So this is going to be 1. Let's see. You could also consider the case when n is smaller than k. So let's say I have n comma k where n is smaller than k.
Madoka will never get to
will always get the worst guy out there to win, right? Because you're going to get the whole tree, which means it is, what is the answer there? 2 to the n, right? Because there are only 2 to the n players. So these are your base cases. Okay, there's one more base case. I think I wrote it down, and we'll see that in a minute. Is everyone clear about this so far? Good? Okay. Okay, so yeah, this is essentially what I wrote down. T of n comma k is t of n minus 1 comma k and n minus 1 comma k minus 1. That's what I wrote down there. But this is the case when n is bigger than k. Then it's similar to the recurrence for n choose k, but it is not the formula for n choose k because the base case is different. And in the over here, we wrote down t of k comma k is 2 to the k, and t of n comma 0 is 1. Both of these were clear to us, right? Whereas for n choose k, that's not the case. In fact, there, if you take t of k comma k, it's how many ways can I pick k items from a set of k items? And that answer is 1, right? That's the number of combinations. So t of k comma k is 1, whereas in our case, t of k comma k is 2 to the k. Very different. And that's why we get different answers from combinations. We also wrote down this, t of n comma k is 2 to the n if n is smaller than k, right? And it turns out you have to use something called dynamic programming to solve this. Some of you may not be quite familiar with it, but it turns out that it's a systematic way of building up the answers from smaller numbers to larger numbers. That's the best way to think about it for now. We'll talk about this more in a more detailed manner. One way to think about this is we start with t of n comma 0, then t of n comma 1, then t of n comma 2, and work our way up. But it turns out even that's not enough. You actually need a matrix of values. So you have to start from t of 0 comma 0, work your way up to t of 0 comma k, and then work down the rows and work your way up to t of n comma 0 all the way up to t of n comma k. And for each one, you use the formula that you have on top, and you can fill this up. Okay? And it turns out that this whole matrix can be filled out, but in the end, you only want this value.
So if you just use like regular recursion, it'd be too slow?
In fact, all you need are for loops. You don't even need recursion.
But you can't use it?
You can use recursion, but then you have to add some pieces to that recursion. You don't want to run the same recursive call more than once, otherwise you'll get exponential time complexities. So dynamic programming with recursion has to be done carefully. We'll talk about that later when we talk about dynamic programming, but for now this is what you have to do. And for every value here, you just apply one of these formula and you're done. Is that clear? And we just systematically fill this up, and every time you fill up a row, you can easily fill the next row because every value depends on values from the previous row. Simple, right? And therefore it all works out. So once you start with the first row, by the way, how do I fill up the first row? What is t of 0 comma 0? First of all, t of 0 means there are how many players?
0.
How many players?
1.
1. 2 to the 0 is 1, right? So there's one player. There's no need for any games. And it doesn't matter what the organizer does with k equals 0. You're still going to have 1, right? So this is 1. And what about t of 0 comma k? You have only one player. And so the answer is still going to be 1. So the first row is just simple. It's all ones. Clear? The second row will depend on values from the first row because that's the formula we have. And you can fill that up and so on until you get to the last row. Is that clear? That's dynamic programming without giving you all the all the details. Okay? Any questions? And once you do this, you will have it figured out. I tried to get a formula, but I did not see one. Did you?
Formula for what?
For T of n comma k?
So the way I computed it is I didn't do
Dynamic programming?
Dynamic programming because it was too slow.
But was it iterative, or was it? Did you have a formula?
So we said like basically this looks like n choose k.
Yeah.
Right? And you can transition from n choose k minus 1 to n choose k in constant time.
Yeah.
You
Which
only-
is same thing here.
Same thing. The only thing you have to worry about the large numbers.
Over there.
Yeah.
Well, over here as well.
Yeah.
Yeah. Yeah, I did not talk about large numbers yet, but basically, applying this formula only takes constant time if you already have these values, right? So if you've got the previous row figured out, every entry in the next row can be done in constant time. Is that clear? And so therefore, essentially and the first row is just all ones, which means I can fill up this entire matrix in time. How much?
Oh, thank you.
N times k, roughly, right? Actually, it's n plus 1 times k, but that's big O of nk, right? So therefore, I'm doing, as you said, I'm doing this in constant time for every entry, and I would have this value figured out in n times k. Do you still see a problem?
So what I'm saying is n times k is still too large. I only computed the last row.
Uh-huh.
I start from n0, and then you can get n1 and up to nk. But I didn't use this.
So if you do n0, that would be, I see.
I had a different sort of, I didn't use recurrence relation.
Yeah.
How did you solve it?
So it's very similar to that idea on the right.
Here. I can rest for a bit.
Do you mind if I erase?
Well, ask them, I don't care.
Okay. Do you mind if I erase? Okay. So I start with the sort of base case when there's n equals 1. And I sort of draw the tree out. Same sort of structure with the left spine, only one winning. There's 2 players. One is here, one always wins. I won't even label the other players because it doesn't really matter. But I make a table just to the side. I'm not actually going to compute this for now. I'm just going to kind of show what I was thinking when I was going through the steps. How many nodes, unique nodes, are at distance 0? There's only 1 in this case, which is always 1. And then how many nodes are at distance 1? There's only 1, right? Now when I grow to, this is n equals 1. When I grow into n equals 2, what I can do is I can basically duplicate this to the right, kind of like how we did before. And then we have sort of another node here for the champion, which is always 1. And this node is not really included. So everything else is basically another distance away. So what I kind of do is I push everything to the right. Duplicate this, but push everything to the right. And now I add up all these values. So I get 1, 2, 1. And I can keep doing this basically for each n over and over again. So for n equals 3, I can compute this again the same way. Make this node equal to 0. This is 1, 2, 1. And then this is 1. I'm just summing down the columns. 3, 3, 1. And then at this point, when I saw this, a very common pattern arose. This is just Pascal's triangle. And what I actually want to get the answer is I want to sum up the rows. This is 0. I want to sum up to k. And you can compute any row of Pascal's triangle in basically O of k time. And that's kind of it.
So Pascal's triangle has combinatorial values, right?
Yeah.
Yes.
Yeah,
Then
choose k.
And choose
you're
k.
saying that it's not equal to combinatorial.
Well, you have to add up the. Yeah.
Add up.
It is actually adding up some n choose k values.
Yeah.
Effectively, but it's not exactly. So yeah, essentially what he's saying is, if I'm not mistaken, is to say that t of n comma k is simply n choose 0 plus n choose 1 plus n choose 2 all the way up to, I think, n choose k or n choose k minus 1. I'm not really sure. I have to check this at the end. This is roughly what it comes to be, and he's saying he can figure this out quickly, and then simply the whole thing is order k time. Is that roughly what you're getting?
Is there a
Yeah,
standard algorithm to use?
Yeah. So because you can write this in terms of this. So if you think about what we were doing, we wrote down t of n comma k. We wrote t of n comma k is t of n minus 1 k minus 1 plus t of n minus 1 k. Right? Now the thing is that this was already figured out on the way to getting here. Right? And this, both of these were, how do I say this? So you could write the recurrence very differently, but by keeping the n the same and reducing k. So I think he's writing the recurrence in this manner and then figuring out how to compute these values. And each of these can be figured out using the previous one in essentially constant time.
Is there a way to get to this expression visually?
This one? Yeah. Yeah, I can tell you how that happens. Is this roughly what you get?
No, yeah, that's exactly.
Yeah, that's exactly right. Yeah. So you're asking how do you get this?
Yeah.
Yeah. Yeah. Well, so if you look at the first k terms, that's t of n comma k minus 1. No. Yeah, I'd have to think about it. Yeah, this kind of comes from, yeah.
He looked at the pattern and just wrote the...
I just look at the pattern and I know that that's just, and Pascal's triangle is just n choose 0 and choose 1.
But it's more than that. Yeah. Yeah, I'd have to think about this.
So even if you do it O of nk, the problem doesn't accept it?
No, and k is too big.
Well, it's expensive because n is already 2 to the 9 or something like this.
I think so.
Yeah. Sorry?
10 to the power 9.
10 to the 9. Sorry. Yeah. Yeah.
How did you solve it? Did you use the same?
But 10 to the 9 is still manageable. But here, trying to store that many itself is going to be a problem. And how big is k?
I think 10 to the 5th.
Okay, then.
N is 10 to the power 5, k is 10 to the power
Okay, that's too much. Yeah. So yeah. So the n to the k will not work out. It'll just crash. Well, it won't crash. It won't accept it. It'll say timeout. Yeah. Yeah. So you would have to use Ricky's idea. Okay. Any questions?
Will you post an explanation to this solution?
It's all live streamed. It's all saved.
No, I'm talking about this approach. Like,
Oh, you mean how do I get this?
Yeah, will you post about it? Or
I could do that. Yeah.
or maybe
Yeah,
you can post it on the
we
Discord.
can work on it. Yeah.
Discord,
Yeah. Sure. Okay. So question is, what other problem you want to see today? And there were some hard questions on the weekend competition, right? Which one?
G.
Sorry?
Question number G.
Question number G. Which one was that?
Add modulo 10.
I didn't look at that one. But there was. Did you try F?
Yeah,
And that's easy.
that's kind of under.
Did you solve it? Okay. So, if I remember correctly, G is yeah, I did not look at this problem. Now, this will take me more time than is there to try and give you some ideas. I did take a look at what was it?
L.
Oh, you had more here, right? Yeah, I looked at some of these. I looked at ocean currents. If you want, I could discuss that. I could also discuss this. I thought the snowflakes one was interesting for others. So if even though you've solved it, I think this may be more tractable for us to cover in the remaining time. So let's take a look at this. Again, what I'm going to do is not worry about the fact that the numbers we deal with are very, very large. Let's ignore that for a second, and then we'll figure out how to deal with the large numbers. Okay. So let me allow you to read the problem. Did you solve this one? Is it okay to have an array of size 10 to the 9? No?
No.
They won't let you?
I think the highest is 10 to the 8th. That's like 256 megabytes, what they let you.
Okay. So let's discuss a solution with the array of size 10 to the 9, and then we'll discuss a better solution later. Okay? Yeah? You read the problem? You want to explain to us, sir?
No, I did it, and Ricky basically explained the solution to me.
I know, but just explain the problem to everyone.
Okay, so you're given integers
Yeah.
sequentially, and you have to figure out the longest sequence where all of the elements are unique.
Okay. Did everyone get that? Yeah? You're given this long stream of integers. You want to know what's the longest stretch of all unique numbers. Good? Because all unique numbers will give you all unique snowflakes, and you can package them and make money. Is that clear? every snowflake, every different snowflake has a different ID, a different integer associated with it. And you want to know, is there a stretch of these numbers that are unique? So let's first look at a simple solution, and then we can look at a fancier solution. All right? So here we have to pay attention to some of these nasty things here in the problem that says every integer can be something in the range 0 through 10 to the 9. Yeah, there are no negative numbers, right? Yeah, 0 to 10 to the 9. And then you're told, well, that's one thing you need to know. If I'm not mistaken, the largest integer you can store is much bigger than 10 to the 9. So that's not really a problem. However, there are other issues, and we'll first figure out a simple solution, and then we'll look at how to improve it. Okay. Any thoughts? Any ideas?
You need a set.
You need a set. You need
Well, you don't
some.
need, but yeah,
Something like a set. So you have to keep track of what numbers are coming in, and then you have to know whether you've seen it before, because you're worrying about uniqueness, right? So somewhere you have to worry about this uniqueness. Let's not worry about hashing or something. Let's just say that we can keep track of uniqueness. So the simplest way to deal with this is to have an array of size 10 to the 9 and keep track of what you've seen, right? And we can fix that problem a little bit later. For now, so assume that you have an array of size 10 to the 9. By the way, you can also have a bit array of size 10 to the 9, which is the same as a set. And you can manage all of this using bit arrays. But right now, let's not worry about this. Let's just assume that you have an array of 10 to the 9, and they are fine. Essentially, it keeps track of which one you've seen and where. Okay. So how does that work? What we're going to do is we have an input sequence, right? Which is, how big is that?
no more than a million.
No more than a million. Well, no, it says, oh, okay, no more than a million. Okay, fine. So this is at most a million long. Okay, so these are all your snowflakes. So here is snowflake 1, snowflake 2, all the way up to snowflake n. Right? You're going to be looking at these snowflakes, and let's consider this simple solution. As I see the snowflakes, I'm going to turn on. I'm going to either say that I've seen the snowflake or not. And let's also assume that I know where I found it. So let's say this is S1, let's say this is S2, and so on. Okay? Then what? As long as they're unique, I would easily know, because if I see S1 again, here is a pointer. It says, yeah, I saw it earlier, and I saw it at this position, and so I can keep track of this. So as long as things are unique, I would know, and as long as there's a copy, I would easily figure out. So how's that going to help me? What do I do?
It tells you when to stop, like.
Yeah, but how does it help me to solve the problem of longest unique subsequence? Right?
So
So let's say you find a duplicate.
Yeah.
Then you have to look at this array. You
Yeah.
see the position that this duplicate is in previously. So you have to delete everything from that.
That's right. That's right. So what I'm going to do is in this sequence, I'm going to have 2 pointers. One where I'm looking at currently. Okay. Another where you'll see what happens. Sorry?
Another when the last unique came.
Right, right. So initially, we're going to assume all of these are unique. Right? The first time that something non-unique shows up, we know that that non-unique must have been somewhere over here, right? What we're going to do is we're going to throw away all of this, including this non-unique one, and only keep things from here. So we're going to have a left pointer that's over here, then we have a current pointer that's over here. So this is left, and this is current. Is that clear? So I have a current pointer and a left pointer that indicates all the things that are sitting in this array. And all the things to the left, I'm going to remove them. And removing is easy because there's only one copy of it, right? I never allow more than one copy in my array. So the moment I see a copy, I'm going to throw away that and everything to the left of it. And essentially, I have to go over those items and physically remove them, which means I'm going to turn these flags off. So think of it as a flag that says, was it there or not? And when I find it, I'm just going to remove it. Good? So that means at any given time, some portion of this array is going to be sitting in, some portion of the input stream is going to be sitting in my array. And I will have a count of how many unique items are there currently in that array. So I have a separate counter here that says current number of unique items. And I'll have another number here that says best number of unique items I've seen so far. Right? So I use that to go through this entire input stream. And at the end of it, I'll just report that number. Is this clear? Okay. So essentially, there were 2 pointers that only move to the right, which means it's a big O of n operation. And I used an array. And that array is kind of big, but I have to initialize it to all zeros. Once I've done that, I'm kind of done, right? Oh, what happened here? Okay. There you go. Yeah. So essentially, the time complexity is proportional to the length of this input string, which is at most 1,000,000 items. Not a problem. But this array is 1,000,000,000 items, and that's a problem. One way around it is to use 1,000,000,000 bits. And that will make this much more compact. But then you have to work with bit operations. There are other ways to do this as well. But for now, I would say think of this as 1,000,000,000 bits, which may be more manageable. If you divide that by 64, it'll be, how much did you say is the biggest array that it'll allow?
I said 10 to the 8.
10 to the 8. So 10 to the 9 divided by 64 should be okay with me, right? Yeah. So essentially think of each of these to be a bit, a 0 or a 1, and all I have to do is to look whether that bit is a 0 or a 1, and then if it says 1, it means it's already present. Then I have to move my left arrow until I hit the current number. So all that is easily done, and I can run this algorithm in the time that's needed. You believe this? Are you okay with the solution? You have a better one? You have a different one?
Same exact solution, just instead of using the bit array, use like hash map or whatever data structure you like.
Yeah. So yeah, the problem with hash map is I have no idea how it gets implemented under the hood, and there's it may or may not work. So yeah, the bit array is a little more work. You have to convert. If you want the 49th item, you have to figure out where that bit comes in, and do some arithmetic, and then figure out what that number is, and you have to do some bit operations. But it's not all that complicated. Can be done, right?
What about the number 64 all about?
Sorry?
You said something, number 64.
Yeah, if you have a 64-bit machine, then your integer takes. This largest integer you store is 64 bits. So I'm going to take 10 to the 9, array of size 10 to the 9. Each one is only 1 bit. So I can store the first 64 items in one integer, right? So the number of integers I need to store this array is 10 to the 9 divided by 64. Correct? Which, according to him, would be acceptable in Java. Is it?
Sure.
Or
I'll have to see, but what about Boolean C++?
Boolean is also bit array in the end. So same thing. Yeah, you could do a Boolean array and see if it works. Yeah, think of this as a Boolean array. Yeah, absolutely. Is that clear? You think you can write this up? It's just 2 for loops. Oh, well, actually, it's only 1 for loop. No, 2 for loops. So there is a for loop for the current guy, which goes from start to end. And then behind it is this other pointer called the left, which starts at the left end, 0.
You just need the length, right?
The length is stored in these 2 numbers. I'm not concerned about it. As I add more things, I'm going to increase the counters. As I remove things, I'm going to decrease the counters. Simple.
Yeah.
Those are straightforward. Right? You see all the pieces in your head? Sure? Then you should be able to write it. Right? Okay. How am I doing with time? I think I am about 9 minutes from finish. Are there other questions that you? So is this the solution you also had, or you had something different?
I used set.
You used the set. So yeah, so there are data structures that you can use. If you know how it's implemented underneath, then you're in good shape. At least in some of the systems, I know that sets are implemented as bit arrays, and so it works. But I don't know if that's necessarily true for all implementations of the Java virtual machine.
Set in Java?
No, C++.
C++, yeah. Yeah. And so I don't know how efficient it is. So you may have various issues, but you can do this from scratch using a bit array for sure.
I think set in C++ is AVL tree, so logarithmic time.
I see. But then you might have space issues because you have a pointer for every item.
Only keep one, still use the 2 pointers, but keep deleting until you see.
No, but your AVL tree is on what? Oh, it's only on the items sitting in the data structure. Yes. I see. Yeah, you could do that. You could do that here also.
Yeah.
So you could take all the items that are present here and store it as an AVL tree. Yeah, that would cost you log n extra, and log n on 10 to the 9 is fine. Yeah, okay, that works as well. Okay, so this modified version is instead of an array with bits, I'm going to remove that and instead store a balanced binary search tree. This balanced binary search tree is only going to have the elements that are present here. So, and it can handle inserts and deletes in log n time, right? And so, as my current moves up, I'm going to insert new items into the tree. As my left moves, I'm going to remove things from the tree. Both take log n time. And both C++ and Java allow you to directly use whatever balanced binary search trees. You have red-black trees that you guys have seen in class, and or you have AVL trees that you could use that are built into the system. Yeah? That's an extra cost. The bit arrays are actually a little bit, they cost less because here you have a random access instead of a log n search. Is that clear? Some of you still look dazed. Are you going to ask me questions, or Demba is lost?
Oh, no,
you solved this already?
Yeah, I solved it.
Okay. Any questions? Are you okay with this?
Yeah.
All right. Then let's stop here today. Thank you.